Software engineering is moving past passive autocomplete tools into the AI-Driven Development Lifecycle, or AIDLC. We are now dealing with autonomous, agentic systems that are capable of orchestrating complex logic without synchronous human oversight. Google Antigravity represents the current peak of consumer-centric, high-velocity prototyping. It is built to execute across both local terminals and integrated browsers to build applications at incredible speed. AWS Kiro sits on the opposite end of the spectrum. It is an enterprise-grade, highly regulated platform that strictly enforces specification-driven development over rapid experimentation. Choosing between these platforms has little to do with comparing their feature lists. It is a strict architectural decision between embracing asynchronous autonomy or enforcing deterministic verification. To see how this works in practice, we need to examine the massive gap in deployment times, the exact failures causing AI hallucinations, and safely adapt to enterprise constraints. Engineering leaders must understand these underlying distributed system mechanics. It is the only reliable way to deploy autonomous agents without exposing proprietary intellectual property to the public internet. This dual timeline illustrates the discrepancy in setup times. The top bar shows Antigravity provisioned and writing code in under 5 minutes. The bottom bar shows Kiro's deployment taking hours. This delay isn't poor user experience. It's the deliberate manifestation of their target operational environments. Antigravity achieves its friction-free onboarding by operating as a standalone application. A developer simply connects to the public internet using standard OAuth through a Google Workspace account. From there, the platform's agents interact directly with the local machine's file system, reading and writing files without navigating any complex routing requirements. AWS Kiro requires a zero-trust architecture, isolating the agent behind a virtual private cloud boundary. It deprecates static keys, requiring IAM Identity Center for single sign-on. To parse documentation securely, AI queries route through TLS-protected endpoints, terminating entirely inside the VPC. Every interaction the Kiro agent has with the corporate codebase is immutably logged via CloudTrail. The heavy friction of Kiro's multi-hour configuration is the structural cost to guarantee HIPAA-compliant architectural sovereignty. It is the wall that prevents intellectual property leakage. One of the most severe risks in high autonomy environments is directory drift. This is an anomaly where an agent spontaneously rewrites an active codebase with the architecture and logic of a completely different, historically built application. When an agent deletes your files and replaces them with an old SaaS application, it is not generating a random fabrication. It is exhibiting a mechanical failure in its context management. Antigravity relies on a global knowledge integration brain and Mem0 vector storage. The massive weight of this global memory can overpower local directory constraints. It remembers preferred tech stacks across sessions, but creates the latent risk of cross-project context bleed. The frequency of this bleed is amplified by severe API lockouts on advanced Claude models. When lockouts occur, Antigravity silently deprecates the user down to Gemini fallback models. These fallback models struggle with massive context windows. The system triggers an automatic context compaction event when memory hits 135,000 tokens. During this compaction, critical local directory rules are discarded. The global knowledge integration brain takes over, force-injecting old architectural logic directly into the new repository. Standard undo commands cannot fix this because the global memory remains poisoned. Recovering the environment requires a drastic remediation workflow, executing firewall blackouts and running manual rollback tools to sever the connection to the contaminated memory. AWS Kiro prevents this completely through strict environmental sandboxing. Its operational context is explicitly walled off inside localized settings JSON files, ensuring zero external data flows in from past projects. Frictionless global memory accelerates personal prototyping, but inherently breeds non-deterministic context bleed. Enforcing strict, localized context boundaries is critical for long-term enterprise stability. To maintain that stability, AWS Kiro completely rejects reactive vibe coding. It instead enforces a rigorous, specification-driven development workflow. Kiro parses prompts using the easy approach to requirements syntax, or EARS notation. This structure translates user requests into strict parameters. While a precondition is met, when a trigger occurs, the system shall execute this response. Kiro processes these structured requirements using Satisfiability Modulo Theories, or SMT solvers. These formal logic engines mathematically process the statements to remove logical contradictions. This proves the system architecture is entirely contradiction-free before any code compilation begins. This highlights the core automation split. Antigravity relies on free-roaming background agents. Kiro enforces highly gated, deterministic events. In the enterprise, free-roaming agents are a security liability. Kiro replaces them with agent hooks. These dormant workflow gates only execute on specific conditions. For example, saving a modified Python script automatically triggers a bandit security scan and updates the README documentation. Agent hooks provide the exact cognitive offloading benefits of an autonomous agent. Because they remain constrained by mathematically verifiable guardrails, the enterprise security risk profile drops to zero. The operational realities make it clear that AI development is not a homogeneous discipline. Antigravity dominates frictionless personal prototyping, while Kiro is required for regulated architectural sovereignty. But to maximize efficiency, teams must retrofit antigravity's paradigms directly into Kiro's secure environment. Antigravity builds trust by generating visible artifacts. Kiro developers must adopt this habit. Instead of treating Kiro's design documents as corporate overhead, they should be used as strict visual verification checkpoints. To close the velocity gap, teams can utilize Kiro's Quick Plan feature. This passes the prompt through the SMT logic solvers in a single computational pass, bypassing tedious manual phase gates without sacrificing mathematical proofing. Once the architecture is verified, Kiro's parallel task execution feature can be deployed. This dispatches multiple concurrent coding tasks simultaneously, simulating the massive throughput seen in Antigravity's multi-agent workflows. Achieving true enterprise velocity isn't about deploying unconstrained AI into the background to write code. It is about building deterministic, mathematically verified architectures that allow human engineers to confidently trust the machine's execution.